Hey Pat, what do you want to do today?
I don't know, blow bubbles or play tag
Or we could go work at the Krusty Krab.
and hang out with Squidward?
Yeah! All you have to do is go to Krabby Patty School, and then Mr. Krab will pay you one whole hamburger a day. Welcome to Krabby Patty School, the #1 education in Bikini Bottom. Who wants to learn how to cook a Krabby Patty today?
I do.
To start off, we obtain a Krabby Patty with a thermal conductivity of 0.5 watts per meter Kelvin.
Thermal conductivity?
Conductivity is how easily a material transfers heat. So for a Krabby Patty, we want a meat that has a high thermal conductivity, so it won't take as long to cook.
Boy, I love learning.
Next, we place the Krabby Patty on the grill, and it's cooked through conduction. Patrick, do you know what conduction is?
Huh, what? Jellyfish?
No, Patrick. Conduction is heat transfer caused by random molecular motion when two surfaces are in contact with each other, like the patty and the grill. The heat passes from the stove into the grill, and the equation for conduction is -K dt dx. So it passes from the stove through the patty, and this is the temperature difference from here to here, and then this is also the distance for x. And K is your thermal conductivity of 0.5. Pat, are you ready for your second day of Krabby Patty School? Pay attention, because today we're going to learn about convection, which is really important. Convection is the bulk fluid motion as well as the random molecular motion of molecules. It's governed by this governing equation where the heat flux is equal to the convective heat transfer coefficient multiplied by the difference between the surface temperature and the bulk fluid motion temperature. The convective heat transfer coefficient is in units of watts per meter squared Kelvin. And like when we look at this, when we're talking about like the Krusty Krab, here's the Krusty Krab. And then the ocean is on the outside of the Krusty Krab flowing by like this. This is our bulk fluid motion. And then this would be our temperature of the surface, and this is the temperature of the bulk. It's important to note that the flux is, the H is dependent on how fast the ocean is moving. So when the ocean's moving really fast, there's more heat transfer to the Krusty Krab, and when it's moving really slowly, there's less heat transfer. Okay, Patrick, now pay attention because I'm going to tell you the Krabby Patty formula. Remember though, you can't tell anyone.
What about Plankton? He asked me to tell him the formula.
No, not Plankton. Of course not Plankton.
Ow!
Plankton!
Well. Looks like I'll be taking the formula anyway, using my constant heat flux gun of 100 watts per meter squared. Oh no, not radiation! Wait, what's radiation? Patrick, you buffoon! Radiation is the heat transfer by electromagnetic waves, or photons. It does not require a medium to travel through. Radiation is governed by this equation, where the heat flux is dependent on the emissivity of the material we're working with, times Boltzmann's constant, times the surface temperature to the fourth, minus the surrounding temperature to the fourth. Ha ha ha. Karen told me I need to relax a little for my cholesterol, so I'll tell you what. If you can solve this heat transfer problem, by the time I get back from my date, I will not melt all the jellyfish with my radiation gun.
Oh no, not the jellyfish!
Yes, your jellyfish. If you can solve this problem, I won't set off my radiation gun. If I shoot the radiation gun inside the Krusty Krab with a constant flux of 100 watts per meter squared and a surface temperature of 600 degrees Celsius, what will be the temperature at the jellyfish fields?
Okay, Pat, so to solve this problem, you're going to need to use shell balances. So we're going to start out with the basics of shell balances. So here we have just a box, X, Y, and Z, and you're going to look at a thin shell in the box, which is indicated by this. And you're going to look at the flux that passed through this shell. So you're going to look at the energy in, the energy out, the generation, and the energy storage of this thin shell within the box. So you're going to do flux times the area, because that's energy, at X, minus flux times the area at x plus delta x. So that's in minus out. And then you're going to do the same thing for y and z. And then this is your generation term. And then this is your energy storage term. So then the next step in this is you're going to divide this equation through by the volume, which is just delta x, delta y, delta z. So then over here, you just get a delta x on the bottom, delta y on the bottom, delta z on the bottom, and you just get generation and then the energy storage term. Next, you're going to take the limit as delta x approaches 0, and then delta y approaches 0, and delta z approaches 0. When you do this, you get definition of a derivative for the heat flux at x, y, and z, and then you just get the generation term and the storage term. If you plug in the constituent, like Fourier's law, the constituent equation for heat transfer, which is this, you get the final shell balance equation, or the heat transfer equation. From here, there's some common assumptions that we usually make. Usually we assume that heat transfer is only in the x direction, so you can cross out y and z. If there's no storage, energy storage, then this is 0. And also if there's no generation, then this is 0. And then you get just the derivative of Fourier's law in the x direction is equal to 0. And if you integrate both sides, you get k dt dx is equal to c, or that the heat flux through the box is constant. So now we'll go over how to use a shell balance on a sphere, like in our Krabby Patty situation. So to begin, you use the same method, assuming that the energy storage is 0 and the generation is 0. And then you get to this equation, which is just again our heat flux times our area, which is the area of a sphere, minus the heat flux times the area at r plus delta r. And then you divide that by the volume of the thin shell. And in this case, this is the equation for the volume of the thin shell, and this comes from the volume of the outside minus the volume of the inside. And when you do this actually out, you're going to get a delta r squared and a delta r cubed, and you can just neglect those because they're so small compared to the rest of the equation. From here, you just integrate, and you take the derivative and you integrate, and you come to this equation, and you can solve for the temperature outside using this equation. It is important to note, though, that in this equation, you can cancel out the 4 pi's, but you can't cancel out the r squares because they're changing.
So before we start our problem, we need to get all of our values for the problem. These are all the givens from before in the problem, and then we're going to use a thermal conductivity for the wood equal to 0.35 watts per meter Kelvin, thermal conductivity of the water as 0.68 watts per meter Kelvin, since we're assuming it's stationary, and then a conductive heat transfer coefficient for the jellyfish of 1,000 watts per meter squared Kelvin. Next, we have our assumptions. First of all, we're going to assume steady state, which means that our flux will only be occurring at the surface of the Krusty Krab, since we'll assume all the generation is occurring inside of the Krusty Krab. We have a constant volumetric generation. We have 1D heat transfer, which means it's only going out in the R direction. And we have constant properties for everything, and the water is stagnant in the ocean until reaching the jellyfish, since jellyfish move.
Go.
So now that we've simplified our shell problem for the spherical problem, we get that our flux for the radius times the r squared is equal to a constant throughout the whole problem. So that way we can know that the flux for the Krusty Krab times the radius squared of the Krusty Krab is equal to the flux of the water times the radius squared of the water. That way we can simplify down and integrate to get the temperature difference in terms of our k value, the flux of the Krusty Krab, the radius of the Krusty Krab squared, and the difference of the inverse of the radii. That way we can simplify down and get all of our temperatures in terms of our flux for the Krusty Krab times the radius squared. Then we'll go ahead for our convective heat transfer, and we can get our h value times the temperature difference is equal to the flux for the Krusty Krab times r squared over the radius of the jellyfish squared. So finally we get our temperature difference in terms of our heat flux of the Krusty Krab, and this allows us to solve for the temperatures of the Krusty Krab and the jellyfish.
Go.
And now that we have our final equation for the temperature, we can solve for the temperature of the jellyfish by plugging in all of our values, and then we get 97.6 degrees Celsius as the temperature for the jellyfish.